Okay, in this video, I'm going to be going over just 3 somewhat challenging mechanism practice problems. The idea that you'll get a little bit of an introduction to these more challenging type mechanism problems, and also work on just understanding how mechanisms work. So to get into the first one, the first thing that's going to happen is you're going to take the highest energy thing, so that's going to be that proton. Why don't I do this in like a green color? So you're going to let that proton protonate our carbonyl, just like that. So protonating our carbonyl leaves us with what's down here in green. So we're at this point. Now, if we ever have the option to make something aromatic, that's going to be a good thing to do. So a good step towards making this ring aromatic would be to move this double bond to, or I'm sorry, this single bond kind of to what would be like a beta position of this double bond. And when you do that, we're going to end up satisfying that oxygen's charge, which is a good thing here. So drawing what we have now. And now we have a positive charge right here. So this is what we have going on. And now the final step to get it all the way to its product is simply let the conjugate base of whatever the acid was. So I'm just going to say water. So I'm going to let water come, pull off this proton. So when water pulls off that proton, electrons will be pushed down and making that aromatic ring. You're regenerating your acid. We don't really care too much about that, but this is how we would get our mechanism to our final product. Okay, so on this problem, we have a tricyclic molecule, and we're trying to turn something that is bicyclic. And it looks like we might be changing a functional group. So go ahead and give this one a try real quick, and then we will work out the mechanism on the board together. So for this problem, when I see something like sodium hydroxide and an ester together, I'm immediately thinking due to saponification. So that's where I will lead off going. So saponification does something like this. I can draw the product down here. So looks like our rings haven't changed. And we have that OH that we just attached and an O minus. So to complete this saponification, we should kick out what was that ester part of our, so that the O single bond to a carbon. We're going to kick that out by reforming a carbonyl, doing something like that. So our new product. And you could also write acetic acid is the byproduct, and I guess I can do that because I have enough space. And that kind of answers where our acetic acid comes from. So that's one part done. Now at this point, we already know what we want to get to, so we can even just look at that and recognize that if we formed a double bond right here, we'd have to break this single bond in order to make carbon have less than 5 bonds to it. So let's break it such that we can form an enolate. So forming our enolate. And I have one too many bonds. I am drawing it kind of messy, but hopefully you guys get the idea. I'll go ahead and also heavy dot some of the carbons. So it's 1, 2, 3, 4, 5, 6, 7. So there's 7 carbons here. We formed a carbonyl right here, and there is a enolate right here. So at this point, we're actually about done. Recognizing that this group in green, so this group right here, recognizing it's an enolate, we can just simply say tautomerization, which is what I'm going to do. I'm going to say tautomerization. And the reason we can do that is because we recognize it's an enolate in a basic environment where you're going to have some conjugate acids being made. You can assume that your enolate will be protonated into its enol, and then the enol will tautomerize into its keto form. So if you imagine that this was instead its keto form, we'd see that, well, our 7-carbon ring, we can check up here. So there's 1, 2, 3, 4, 5, 6, 7 with clearly a 5-member ring attached right next to it. And that's the same thing as we have down at the bottom. So this would be our full mechanism for this problem. Okay, so here's another quick one. Again, we're not given very much, just sodium borohydride, which, excuse me, but for us, we will just refer to as H minus. So try to figure this mechanism out real quick, and we will work on it after. So for this problem, sodium borohydride, a source of H minus, I'm thinking I'm going to use it as a strong nucleophile. So remembering that you have the option of weak nucleophile and strong nucleophile if given an alpha beta unsaturated carbonyl. So that's what we're dealing with here. I'm going to let this source of H minus attack this carbonyl at its 2 position. The reason I picked this carbonyl is because the ester carbonyl is a little bit less partially positive. And so the partial positive of this carbonyl is going to be greater, and it'll attract that H minus a little bit more. So at this point, we have this sort of thing going on here. So let me just make sure I have my carbons right. I'm going to do another heavy dotting. So 1, 2, 3, 4, 5, 6, and the oxygen is 7. Perfect. So at this point, now we're going to simply do just an esterification. So allowing the electrons from this oxygen to bend around across your ring system. You can hit that carbonyl. And now we're just doing the mechanism for Fischer esterification at this point. So double bond still there. And I have one too many bonds to this carbonyl. So it should be O minus because we've connected it to that oxygen. Now complete Fischer esterification by kicking out the other group. So kicking out the other group leaves us with what will be a 5-member ring with, well, the oxygen's 1, 2, 3 carbons hanging off of it, or 3 atoms hanging off of it, excuse me. So we are at this point. So there's our 3 atoms. And now the final step to get to its product is just to let something acidic come and protonate it. So I'm going to just signify that as H plus here. So H plus right there. And now protonation. And that gets you all the way to your final product. So this is our mechanism for this problem.